right, so welcome back after lunch. I'm Peter. I'm going to talk about proving information flow security in concurrent programs. And I would like to start by giving you a very brief motivating quote that shows why we should care about the topic. So in 21, there was a security breach in Microsoft Azure, the cloud of Microsoft. And Microsoft Security Response Center put out the following message afterwards. They said, our investigation found that a consumer signing system crash in April of 21 resulted in a snapshot of the crashed process, a crash dump. The crash dumps, which redact sensitive information, should not include the signing key. In this case, a race condition allowed the key to be present in the crash dump. This issue has been corrected. So this kind of example shows that, first of all, we should care about having secure information flow properties in our programs, and second, it matters to look at this topic in a concurrent setting because concurrency could cause information to leak. So if you step back a bit, so what I would like to do is I would like to look at systems where we assume that the systems manipulate certain public information, typically called low information, low sensitivity information, and secret information, also called high information. And we would like to be able to verify that an attacker cannot interact with the system and thereby learn anything about those secrets. And so the simplest way for an attacker to learn about secrets is a so-called value channel. And I illustrate this with this program here. So in this little function, compute, I take two inputs. H will always be a so-called high sensitivity or secret input. And L is always going to be a low sensitive or public input. Right? And for such a program, we would like to answer the question, well, does this program leak any information? In this case, it seems fairly obvious that it does, right? Because we branch on the secret, and depending on whether the secret is positive or not, we leak or we return different outputs, so we can learn something about the secret by looking at the output. So the way this is typically formalized in verification is as a non-interference property. So that means we look at two executions of this program. In my slides, there's always going to be a blue execution and an orange execution. And we say, well, if those two executions agree on all the low input values, now we execute the program twice, is it then the case that the low output values also agree? In other words, does a different secret not have any impact on the output value that you get in the end? And so in this particular example, if we look at one execution where the secret is positive, we get the result 1, and another one where the secret is not positive, in this case 0, we get the output 2. So obviously the result is different, and so therefore we know that there's a value channel here. The attacker can learn something about the secret input. So now besides value channels, there are of course so-called side channels, right, that we also need to worry about, and the most important kind of side channel is a timing channel. Let me also illustrate that with this program. So again, I have a secret input H and a public input L. And what's happening here is that we always return the same value, right? So the result value does not really tell us anything about the secret. But the execution time depends on the secret because we branch on the secret here and we have more instructions to be executed when the secret is positive. So if again, when we look at the two executions and we have an attacker that can observe timing differences, the observer can possibly learn something about the secret by just observing time. All right, so also in this case now, this would be insecure if we have such an attack. Now the point of my talk really is that I would like to not reason about timings, because reasoning about timings or proving property of timings is extremely difficult, right? We execute these programs on very complex hardware. We have things like caching and pipelining and speculative execution, and we have instructions whose execution time depends on operands. So it's not just branching on secrets, it's also like dividing by a secret, which could influence your execution time. We have compilers that do all kinds of clever optimizations. So reasoning about timing is really, really hard. And in some cases, we have to do that, like for instance, when you verify a crypto library. But fortunately, in many other cases, you don't, right? Because sometimes you compute data that gets published only later, a bit after the execution has finished, as you cannot really measure the timing anymore. Or maybe the timing measurements will be so imprecise because, for instance, it happens over a laggy network that you cannot really conclude much from that. So in this particular talk, I would really like to reason about the absence of channels, but I do not want to reason about timing explicitly. So our goal is that we would like to deal with an attacker that can observe the final result of our computation, but not intermediate values. So the attacker is not sitting on our machine observing our heap and stack. And the observer in particular can also, the attacker can also not observe timing. So that's our attacker model for the purpose of this talk. And now the problem is that this nice separation between a value channel and a timing channel unfortunately gets completely blurred as soon as you go to shared state concurrency. And this example illustrates that, right? So we have a parallel composition here, right? On the left side, we initialize a value I to 0, and then we iterate up to the secret. And then after this loop has terminated, we assign 6 to a shared variable. And on the right-hand side, we have a variable j. We count up to 100, and then we assign 7. Let's not worry about data races here. Let's just ignore those. And so then we return the shared value. So what we observe here is that we have one thread whose execution time depends on the secret, and the other one whose execution time doesn't, right? And now even if you have an attacker that cannot observe timings, they can still see a difference, because if you look at two executions and you look at an execution here where age is very small, then most likely the thread on the right will run longer, right? And therefore the last assignment that's going to happen to shared is 7, and most likely the result is going to be 7. Whereas if you have an input that is a rather large value, then it's likely that the left thread will run longer. So this assignment is going to be the last one that's being executed, and the final value will be 6. And now even if you have an attacker that does not observe timing, at least probabilistically, they learn something about the circuit. So what shared memory concurrency does, it really turns timing differences into value channels. Okay, and what I would like to do in this talk is that's our goal, I would like to verify the absence of value channels in a concurrent program, but still without reasoning about timing, because that's very, very hard. Okay, so that's the goal that I'm trying to address in this work. So let's take a closer look. So this is the example we looked at before, and let's see where really this leakage of information comes from. So what we have here is we have a secret value, age, and that secret value influences the execution time because it's used in the guard of a loop. And the execution time might influence the order in which modifications of the shared data are performed. So maybe this assignment is performed first, or maybe that one is performed first, right? In the order of those modifications ultimately determines the final value of the shared variable. So you have kind of this causal chain that leads from the secret value to the observed value that the attacker can see. And now existing work on logics in this space, on modular verification of secure information flow, basically all try to prevent such leakage by breaking the very first causal dependency here, right? They basically say it should not be possible for a secret value to influence execution time. And the way they typically do that is by simply disallowing branching on secrets. But that is not really sound on realistic hardware, right? As I just mentioned earlier, we, for instance, have also operations whose runtime depends just on operands. So even if it's not a branching involved, you might still have timing differences. So this is not quite enough on realistic hardware, and it's also overly restrictive. So let me show you another example. So this example is also going to be ruled out by existing work, but it's actually secure. So let's take a look why. So here we initialize our shared variable to some low value L, doesn't matter what it is. And then again, we have two threads, and one of them has a secret depending timing. And after the loop on the left here, I increment my shared variable by 6, and on the right, I increment it by 7. Okay. And now it turns out when you run this program, this is actually secure, right? Because in the end, in both cases, the final value of shared will be L plus 13. So it doesn't really matter which of the thread runs longer or shorter. Yeah?
Are you assuming atomic increments?
Yeah, I assume atomicity here. I will make this more explicit a bit later in my talk. But for now, let's just assume that both the assignments and the additions here are atomic.
Another question, so if you rule out data races altogether, do you still have potential problems?
Yes. So just imagine that on both sides you acquire the lock, you access shared, you release the lock, you have exactly the same behavior, right? So I just really try to not clutter up my slides too much. That's why I just live with the data races here, but it doesn't matter. All right, so what we see here is that by just, trying to break the dependency chain here at the top, we are first, not really solving the problem because it's not sound on actual hardware. And second, it's overly restrictive. So in this particular example, this would be rejected even though it's perfectly secure. If you step back a bit, well, why is this secure? Then we see that, well, this is really because the operations on the shared state here commute, all right? And even though if you have timing differences between the two different threads and therefore different orders of updates, it doesn't matter because those modifications commute and therefore you don't have any information leak here. So the first key idea of this work is we would like to exploit commutativity because if we know that the thread schedule does not, let me just read it out. Because we know that the thread schedule does not influence the final result if all the modifications of our shared data commute. So that's how we will tackle this problem. So in other words, if we look at this causal chain again, instead of trying to break it at the very top, we break it at the very bottom, right? So we allow these different execution times, we allow different orders of modifications, but we make sure that these different orders do not affect the final value in the end. And so with this idea, this example would correctly verify because our two increments here obviously commute, addition commutes, so this could be verified as being secure. Whereas if you look at the other program we had first, because assignments don't commute, this would still correctly be rejected. Okay, so what I'm going to do now is I will give you a very high-level intuitive idea how this verification idea works. Then I'm going to sketch a logic that implements, realizes that idea, and then we'll make this whole idea a bit more practical as we will discuss later. So what's the high-level idea? Yeah.
Going back, can you give us some more clue sort of where or how often you would expect this commutativity to arise in examples?
Yeah, that's why I just said I will show later how we make this more practical. So I'm aware that there are not so many commutative operations in our programs, but we will relax this requirement later in a way that makes it much more applicable. So if you can be patient, then I'm going to answer this question later. Okay? All right, so let's look at the overall setting. So we look at a situation where we have some shared state. Then we have a parallel composition, and on each side of this parallel composition, we execute a bunch of atomic operations. And now I make these atomic operations as explicit by really putting this atomic keyword in front of it. And you could imagine that there's some suitable synchronization that makes sure that they're actually atomic, or maybe this is something like a compare and swap or something like that. And now what we do is we impose three different proof obligations. So again, we look at two executions, a blue execution where maybe the thread interleaving is ABC, and an orange execution where maybe the interleaving is BAC, doesn't matter. And so we prove three things. First, we impose a proof obligation that at the beginning of the parallel composition, the value in both executions of the shared data is the same. Okay, that's step one. Second proof obligation is to say that both executions execute or perform the same updates on the shared state. I will make more explicit later what same update really means, but for now, intuitively, here we have operations ABC, here we have operations ABC that perform the same updates. And finally, we prove that all those updates actually commute. So A and B and C pairwise commute. And if those three proof obligations go through, then we can conclude that at the end of the parallel composition, so here, the shared variable again is the same in both executions, so it has still a low value and we can treat it as public information. We can leak it if we'd like. So let's look at an example where this would fail, for instance. So imagine that now in this write thread, you have an if in addition to the B operation here. You have an if statement that depending on the secret, you might execute another B operation. Then our executions could look like that. And now the first proof obligation would still succeed because we have the same value L in both executions. But now the second proof obligation would fail because you have an unmatched B operation here, which you don't have in the blue execution. So this would fail, and therefore the program would be rejected because we don't know that the shared data is going to be public after the parallel composition. So that's the high-level idea. So now let me dive a bit deeper into the logic that we use to actually verify such executions. Of course, I cannot go into the full details of the logic, so I'm going to stay at a fairly abstract level, but I hope I'll be able to convey the main ideas how this works. So in our logic, all the assertions relate to states. It's a relational logic, and so this is a separation logic, so we have the usual kinds of assertions, like assertions over local variables, amp points to separating conjunction, and many other things, and there's this low assertion. So most of these assertions are unary assertions, meaning they talk about only one execution, and then the semantics is an assertion holds if this property is true in both executions, right? They don't relate the executions, but in each of them individually, this property needs to hold, right? And the only assertion that really relates the two executions is this low, and low says that expression E evaluates to the same value in both executions. So this is what it means to be public information. And now over these assertions, we define judgments in a Hoare logic. And so they just look like regular Hoare triples. But again, the interpretation is over two program executions. And so intuitively, such a triple holds if, in case you have two executions that start in two states that together satisfy P, then they will not crash. And if they both terminate, then the two resulting states together will satisfy Q. So this is a relational logic that reasons about two executions of the same program and is relating them with those relational assertions. So now let's see how we can bring this idea of commutativity into that logic. And before I do that, let me give you a very, very quick reminder of how we do certain kinds of proofs in separation logic, because we will use that to make our logic actually quite simple. So in separation logic, when you reason about heap data structures, what you typically do is you first abstract your concrete heap data structures, say your linked list, to some mathematical domain, say a sequence of values, and then you describe the semantics of your operations relative to this mathematical abstraction. So that's what you see here. So in the gray box, we have an implementation, say, of a linked list of integers. In yellow, we have a separation logic predicate, which does two things. It describes the footprint of a linked list, and also it tells you how to abstract the linked list to a mathematical sequence. So that's why it takes this sequence as a parameter, and the implementation describes, the definition describes how the concrete implementation is linked to this mathematical value. And now when you look at the specification of, for instance, our add operation on the list, we just specify its functionality by showing how it manipulates the sequence. So if you start out with a list that is abstracted to sequence S, then afterwards it's going to be S concatenated with the element E. So this is just totally standard separation logic, right? And we make use of that. So what we do in our work is we try to lift all the reasoning from the concrete program up to that abstraction that is the sequence here. And we call those abstractions resources. So whenever you have some shared data, something that you manipulate during a concurrent part of the execution, that shared data has to be represented by a so-called resource. So a resource has a name. It defines the type of the abstraction, that's the sequence. It has an invariant, which is really the separation logic predicate relating the actual implementation to the mathematical value. And it has a bunch of so-called actions. So here my only action is append, which has a mathematical definition, namely it's the concatenation on sequences. Yeah?
Sorry, I don't understand what the invariant list XV means. Could you just say a little more?
So this just means that if you take a pointer to a list called X, right, then this will abstract that list to a mathematical value V, and then V shows up again in those rules here. You see this in the next slide that I show you the Hoare logic rule. You will see exactly how this works. And so this basically does not introduce any overhead, right? I'm just taking the standard ingredients of a separation logic proof, right? So the mathematical type sequence is used in the separation logic predicate anyway. the list predicate we would have in separation logic anyway, and the actions here is what we use in pre and post conditions of separation logic proofs anyway. So I'm just collecting those in a sense in one declaration to say our shared state is always represented by such a resource. Okay? And now we can go over our 3 proof obligations, and I can try to show how we prove those 3 different things. Remember, the first proof obligation was to say before you start the parallel composition, the shared variable has to have the same value in both executions. So the way we do this is as follows. So before you can use a shared variable in a parallel composition, you have to explicitly share it. So this is like a ghost instruction that says, well, now we are going to use X in a concurrent piece of code in a shared manner. And so now if you look at the rule here, if you want to have a share, you have to prove that you have the invariant of the appropriate resource. So the list must be there with an abstract value v, whatever that is. And now you see here, this proof obligation reflects that the initial abstract value of the shared data structure must be low, must be the same in the 2 executions. So this is really the first proof obligation. And if you manage to apply this rule, then what you get to assume afterwards is that now the invariant holds again for a possibly different abstract value, right? The sequence of values might have changed, but you get to assume that this new abstract value is again low, so you can still consider this public information and you can leak it later on. So that's basically the first thing we have to prove, and this is the benefit that we get out of this entire verification technique, that we get to assume this low property after the parallel composition. Yeah?
So this is a super pedantic kind of question. The exists v prime needs to be the same v prime in both the runs. You see what I'm saying? So the exists there has to scope over both the traces of the C. I'm just trying to connect it to your earlier slide.
Yes, so every assertion we write is interpreted over pairs of states, right? And so basically you can read this as there exists a value in one state and there exists a value in the other state. And this low here says, in fact, they have to be the same. But if you think about...
So they could be 2 separate values.
In principle, they could be 2 separate values, but this low assertion here tells you they're not. Yep. Yeah, Nick.
So low is the only predicate that is somehow joined, and the others are...
Yes, low is the only thing that really relates to 2 executions. Every other property has to hold in both of the 2 executions. All right? So now this was our first proof obligation, right? When we start out in parallel composition, the abstract value must be low. So for the for simplicity in this rule, I assume that there's only one resource, right? We could have, of course, many such resources, but just for presentation purposes, I assume there's only one resource. Therefore, it's clear which invariant we mean and so on. All right? So that's just for the presentation here. So let's look at the second proof obligation. The second proof obligation was both executions perform the same updates. So now let's see how we can do that. So first of all, we make sure that the only way you can perform an update on the shared variable is via this atomic statement. So therefore, we have this rule which basically says, well, if you want to actually use your invariant, if you want to get this invariant out of your context and actually use it to get the necessary points to predicates to manipulate the data, you need to wrap this inside such an atomic statement, and then you get to use the invariants. And now the interesting thing here is the following. The proof rule describes that when you start out executing this statement C, where your shared variable has some abstract value V, then afterwards it will have an abstract value that can be described by applying a function f to v and some extra arguments e. Now that's in a sense the abstract action that you're performing. Remember, we have the concrete implementation like the add method in the code, and we have the abstract action like append something to a sequence. So f here is this abstract action that we execute. And for simplicity, again, I assume that there's only one single such action. You can easily encode many different actions, but just having an extra parameter that chooses which behavior you want, right? But mathematically, there's just one such action called f, and the parameter here really determines what this action does. So now what this rule really tells us is we have a way of mathematically describing what's happening to our shared state. And now remember, our goal is we want to prove that in both executions we execute the same action. So how do we do that? Well, we generalize this rule a bit. So what we do is in the conclusion of this rule, we track in a separation logic resource all the actions that have been performed. So now if we have only one kind of action, then the only thing we need to track is parameter tuples, right? Every action that is being called is uniquely identified by the parameter tuple that was used, like here the v, e. Now that's exactly what we are doing here. So these actions is a separation logic resource, and args is a multi-set of parameter tuples, right? And now every time we execute an atomic statement, we take the parameters of the action that was being executed and we add it. So this is a multi-set addition. We add it to this set of arguments. So this multi-set of arguments grows over time and in a sense keeps track of all the actions that we performed during the parallel composition. Now that by itself does not yet make sure that we perform the same in both executions. It's just a way of bookkeeping, right? We just record whenever we perform an action what that action was. Nick?
Why did V get dropped in the conclusion?
Yeah, I guess it shouldn't have. Yeah. Yes?
Is there an implicit assumption that the resources are not non-deterministic? That if you have one resource that maps to one underlying representation, or indistinguishable underlying representations through the API?
Yes, so the invariant has to guarantee that, yes. All right, so now how do we make sure that we actually do the same updates in both executions? Now that's again a part of the share rule that you've seen before, so now I'm just making it a bit richer. So when you share something for a parallel composition, then when you go into the parallel composition, you get to assume that so far no actions were performed on the shared state because you just shared it, right? So that means this actions multiset is the empty multiset, right? And now you do your parallel composition. So C is this parallel composition. You do all kinds of steps. And afterwards, you know that now you have some multiset of arguments that represent the actions. And now the proof obligation really says that multiset has to be low. Right? So that means both executions have the same multiset of actions, and so therefore they perform the same actions. And doing that, basically, doing that check only at the end of the share in a very lazy, delayed way actually gives us a lot of extra flexibility because that means we do not have to align the threads of the parallel composition in a fine-grained way. We just let both of them run to the end, and then at the end we prove that the actions were really both in both cases. So yeah, I mentioned all of that. So you'll see an example later on where this actually gives us a lot of flexibility. And now finally yeah, sorry, Ranjit.
I was just curious why the commutativity hypothesis shows up.
That's going to be the third proof obligation. Next one, yeah.
I would have thought if would have played a role somewhere because in your earlier example there was this if h greater than 0 mumble and that was going to be rejected by your system, right? Because there the actions don't line up. So I'm a little surprised. So what happens? There must be some rule for a join. Or what's the rule for if then else that somehow makes sure that you do the same actions in both branches?
Well, every time you do an action, right, then you will add it to your to this multiset here. So what you know about the multiset might depend on your if conditions, right? So then if you need to show that this is always the same, so that kind of reasoning step might take the if conditions into account. But you don't need to account for that separately in the proof. This is just standard Hoare logic reasoning, right? You might take two different branches to the execution, and in every single one of them, you add different things to this args multiset. And now if in the end you sit there with a proof obligation to show that they're always the same, well then you better know that, for instance, your if conditions were low or you have another reason to believe why they're always the same.
It could be the case that both threads have ifs and else, but they do the same ifs and else, and so they have different args. But
yes.
Under the same conditions.
For instance, yeah. I'm going to show you a concrete example in a couple of minutes. All right, so the third proof obligation was to say that the updates actually commute. And we do that also on the level of the separation logic abstraction, right? So we don't show that the actual add methods of the implementation commute. That would be a rather complex program equivalence proof. What we do instead is, well, we know that we have our actions. Our actions have some mathematical representation. And we have a simple proof obligation that says for all argument triples E and E prime, the order in which you perform those actions doesn't matter, gives you the same result. So we prove commutativity on the level of these abstract actions, which is then a simple SNT query. All right, so now we could apply this, and in our running example, for instance, that wouldn't quite work, right? Because in our running example, our append operation does not commute, right? Sequences have an order, and so if you append elements in a different order, you will not get the same result, and that basically takes us back to Peter's questions. I mean, realistically, how many of the operations we typically execute on shared state actually commute? So let me show you that on a concrete example, and that will then be the segue into a relaxation of this technique. So here in this example, I'm going to start out again with a shared list. So initially the list is empty. And then in one branch, in one thread, I have again a secret-dependent loop, and at the end I add 6 to the list. And in the other thread, I have another loop, and at the end I add 7. And then after doing this parallel composition, I return the sorted value of shared. Okay? So now if we apply our technique, we have 2 executions. In one, we might first add 6 and then 7. In the other one, we do it in the other order. So we get 2 different lists here. And therefore, our verification technique as introduced so far would fail, right? We can prove that the initial values are the same. The list will be empty in both executions. We can prove that we perform the same updates. So there the argument triple will be 6 and 7 in the multiset. That would succeed. But if we want to prove commutativity, then of course that fails because addition on or a concatenation of sequences doesn't commute. But on the other hand, if you look at the example is perfectly secure, right? Because before we return the list, we sort it. And no matter whether the intermediate value was 6, 7 or 7, 6, the sorted value will always be the same. So this shows that our technique so far is overly conservative, right? Because it says it really has to be the same value. But sometimes it's not, you don't care so much about the exact value of the shared data structure. You only care about certain aspects of it, okay? And now here comes the second key idea. The second key idea is we put another layer of abstraction on top. So far we just used the standard separation logic abstraction, going from a concrete data structure to some mathematical domain. So now the purpose of this second abstraction is to say, well, often you don't want to leak the entire data structure later on, but only certain aspects. Maybe you sort it first and then the order doesn't matter. Or maybe you do some kind of aggregation. You compute a sum or an average over it, and then the details don't matter, right? So very often what you want to leak is not the whole data structure, but another abstraction of it. So now we build an abstraction on top of the abstraction. And actually that works quite nicely. So if you go back to our basic technique with the concurrency and the different actions, what we do now is the following. As a new step 0, we define this additional abstraction. So think intuitively, this says, well, what part of my data structure will I later want to leak? What do I want to consider to be public? Okay? And once you've done that, now you can, again, look at 2 executions, and you can weaken your 3 proof obligations using this abstraction. So first of all, you just have to show that the abstract value is the same in both executions at the beginning. Second, you have to show that the 2 executions perform the same updates modulo this abstraction, so more things start to commute. And third, you need to prove that all the updates commute only modulo the abstraction. And if those 3 proof obligations succeed, then what you know at the end is that the final value after the concurrent execution is again the same modulo the abstraction. So let me apply this to 2 examples. Several examples, let's say. So here, this is the program again that we looked at a moment ago, right? The one with the sort at the end. Now, how would we verify that? So since we want to return the sorted value, what that means is we only care about the elements in the list, but not their order. So our second abstraction that we put on top of the standard separation logic abstraction could be to say, well, we just look at a multi-set of values, not a sequence anymore. So my abstraction would be a multi-set of integers. And now if I look at my two executions, well, the initial value is always the same. That means it's also the same under abstraction. If I look at the same at the executions, well, both threads perform the same executions anyway, even without the abstraction, so that doesn't really make a difference here. But now the third point is important because under abstraction, the two additions commute, right? If you say the order doesn't matter, it's just a multiset, then it doesn't matter whether you first add 6 and then 7 or vice versa, right? That gives you the same multiset. So because of this extra abstraction here, our operations commute, and therefore this proof obligation goes through. And therefore what we get to find out at the end is that when the parallel composition ends, we know that the multiset of values will be the same in both executions. And if the multiset is the same, then after applying sort, of course, you get the same result in both executions. Okay? And that's why this program is now considered secure, but wasn't in our original technique without the abstraction. Going back to Peter's question, so in our experience, there are lots of examples where you only want to leak certain aspects of a data structure, and so you can often apply quite coarse abstractions, and the coarser your abstraction is, the more things start to commute, even if they don't commute on the concrete level. Let me show you two more examples about this. So, oh, sorry, yeah, question.
Yes,
yeah.
sorry to interrupt, but
No, please.
do you know it relates to observational determinism? There was a series of papers 20 years ago. It's not the same proof technique, but the idea.
It's not the same proof technique. It's related. It's not the same. I'm not sure we should go into this now, but
Okay.
yeah. Yes, Nick.
Under this constraint, I was expecting you would be able to remove the sort.
No, you return shared, right? And so you return the entire list, and the list contains the order.
Since alpha is not necessarily the power of the attacker to observe something about the list.
No, this is just what you, I mean, in your proof, right, you track information, what you know to be low, right? And what you know at this point is you know that alpha of the list is low, but you don't know that the list itself is low. It isn't, in fact, right? So therefore, if you just, well, I mean, of course, your question makes a lot of sense. This example doesn't give you a proof of a post condition. But if, assume for a moment that we have a post condition that says the result is low, right? That would not be true without the sort operation, because the list is not low in both cases. If the post condition says alpha of the result is low, well, then you can prove that, even without the sort.
I think this treating alpha as the kind of power of the attacker, it reminds me of the patterns on the
But it's not, I think it's not the power of the attacker, right? Because the alpha changes for every parallel composition in your program, right? Depending on where you are in your code, you might look at very different abstractions. And if this was the power of the attacker, this would be fixed for the entire system. So this is really something that you use to verify one particular piece of the code. Yeah, Mike?
I sort of was confused about this too. It sort of seems like this alpha thing is, you're sort of making an assumption somewhere, which I assume you will prove, that the attacker can't observe anything other than under that abstraction, or that you have to then say, you know, that sort of thing sort of discharges that proof obligation, because it says two things that are alpha equivalents can't be distinguished by the attacker when they observe this return value. Is that actually like in there, or does that not come out somewhere?
No, it does. So our attacker model was that the attacker can only look at the final result, right? Not intermediate values. So if this is going to be the final result of your program, then the attacker could look at that. You would get a proof obligation that this has to be low. And it wouldn't be low if you didn't apply sort first. And in the implementation, I'm going to talk about it in a moment, we do the same for all I/O operations, right? When you have a print statement somewhere, you need to prove that whatever you print is low. And so then, I mean, you need this kind of information.
Okay, I guess I'm not, maybe I've just missed it, and what that proof obligation looks like, where does the alpha come into that proof obligation, I suppose, is the
It doesn't. It doesn't at all. So the alpha really, so all you need the alpha for is you need to know, or you want to know, that after a parallel composition, something is low, right? And if the thing that is low is what you want to print later in the end, or return to the person running the program, and this is exactly the information you need.
But I suppose the proof obligation that you're going to get is you want to prove that if sort takes two inputs that are alpha related, then the output should be literally the same.
And it really depends on the context in your program. And the high-level proof obligation, so the high-level proof obligation is you have a main method or main function, right? And the main function in the end returns the result of the program, and that thing has to be low. And everything else is just how you structure your proof. And this is a particular way of structuring your proof such that you can show this ultimate lowness of the result of the computation. So maybe you want to prove that sort works on alpha equivalent inputs, maybe you don't. It depends on your complete program, right?
But if this is the complete program, you need to prove that.
If this is the complete program, that what you would have to prove is that what you return here is low.
That means that sort, if you put alpha equivalent inputs in sort, the output should be literally the same. That is the proof obligation you get for this program.
Right, what you would need, well, I would probably not phrase it in terms of alpha. What you need in this particular example is you need to know that when you give two lists into the sort algorithm that are multiset equal, then the result of sort will be the same.
And that's what I said.
Yeah, it's just expressed a bit differently, but that's I think the slight difference between the way you phrased it and the way I phrased it is that my specification of sort does not have to talk about alpha, because alpha is something that I chose for this particular parallel composition. So when I specify sort somewhere else in a library, I do not have to be aware of the alpha. It's rather the other way around. I specify the functionality of sort. That will talk about multiset equality, and that gives me the idea that multiset equality is the alpha that I want to pick here. So the kind of the flow is in a different direction. Yeah?
So there's something I would expect you to need to prove about your actions. Namely that if you take two lists that represent the same multiset and you add the same element to each one, then you get two lists that represent the same multiset. That is, abstraction commutes with addition. But I'm not sure where that is in your proof obligations.
I think that happens in the proof rule that I showed for the second proof obligation. But given that I only have 2 more minutes, I'd love to discuss this in the coffee break to show you precisely where I think this happens. All right, so let me show you 2 more examples that this technique can handle. So imagine that you have a shared map. Again, I have one thread that puts 1,8, so key 1, value 8 into the map, and another one that even puts the secret into the map, right? So that sounds dangerous. But then at the end, we just return the key set of the map and not the values. So now if you have such code and you would like to prove that whatever you return here is actually low, then what you would choose as your abstraction alpha is the domain or the key set of that map. And then you can show that both executions here add the same values to the key set, namely the 1, right? So what kind of key set you get at the end does not depend on the secret, and therefore we can verify that. And so the last example that I want to show is a nice example in the sense that it shows how this delayed checking of this same updates property gives you a lot of flexibility without having to find a precise alignment between different executions. So here again, I start out with an empty map. And in one thread, if the secret is positive, I put 1,8 into the map. And in the other thread, if the secret is not positive, I put 1,8 into the map. And again, I return the key set. And this would also verify, because if you think about it, every execution of this program will put exactly one tuple into the map with a key 1. Maybe it's this one, maybe it's that one, we don't know, it depends on the secret. But no matter what the secret is, you would always put a 1 into the key set. And therefore, the key set does not depend on the secret, and therefore we can verify this program. Okay? And this is only because we check this equality of performed actions after the parallel composition and not during and after the parallel composition, you have the equality there. So I have 10 seconds to go. So all of this is formalized in a PLDI paper, so there you can find the details. We have an implementation based on top of Viper, which handles a lot more. We have dynamic threads. We have, of course, multiple resources. We have I/O operations and a bunch of other things. And 7 seconds to go. In the paper, you will in particular also find a formalization and soundness proof in Isabelle. So if you want to see all the details, you could look it up there, or you can just talk to me in the break. Thank you.